Hello, today we're going to work on chapter 11, our last chapter of the semester, and it's all about comparing two samples. So go ahead and turn in your course pack and let's roll. So chapter 11 is inferences on two population parameters. 11.1 is going to be all about comparing two population proportions. Okay, so qualitative data. So we need to have a little discussion between independent sampling and dependent sampling. And also make sure that you're watching section 1.6 before you watch this chapter. So independent sampling is when the individuals selected for one sample do not dictate or have a relationship with the individuals in the second sample. Dependent sampling is matched pairs. So dependent sampling is when the individuals selected to be in one sample are used to determine the individuals in the second sample. Also note, it is possible for an individual to be matched against themselves. So sometimes we'll have a pre and a post or a before and after. Let's say you start a workout regimen and you weigh yourself before you start the workout regimen, and then 2 or 3 weeks later you weigh yourself again. That's a pre and a post. That's considered matched pairs. Independent samples are 2 independent groups measured once, and dependent samples are 1 group measured twice. This gray box is very important. It's definitely worth a sticky note for your note sheet. So you can think of it like this. Dependent sampling is a population where you take a sample here and a sample here and compare them. Independent sampling is population 1, you take a sample, population 2, you take a sample. Go ahead and turn in your course packs to page 240. And let's look at example 1. It says, decide whether the sampling method is independent or dependent, then determine whether the response variable is qualitative or quantitative. State the type of interval of hypothesis test that would be performed. Okay. So we're going to need our gold sheets out for this as well, because this is going to help guide us. So it says we conduct a survey of 100 random men and women, 100 random women, to find out which was their favorite Summer Olympic sport to watch on TV. And we know that they're independent because they're 2 different samples. They're not in any way related to each other. So this is a possibility, independent, and this is a possibility. And we just ask them what sport they're watching. So that would be qualitative, independent qualitative. Okay, and so then we need to decide what type of test we're going to run. So it's 2 samples that are independent. So we're going to get out our gold sheets here. We're looking at everything in chapter 11. So you're looking for chapter 11. This says 10.2. So we're looking for chapter 11. So here we have some chapter 11 confidence intervals. So here we have chapter 11 proportions, and they need to be independent. So this is matched pairs. That's not what we're doing, and that's means anyway. So we're looking for this 2 prop Z test. Okay, so we're going to be looking for the 2 prop Z test. So letter B, we conduct a poll of 100 random men and 100 random women to find out whether they like watching Olympics on TV or not. We first call them the day before the Olympics start, and then we conduct a follow-up call the day after the Olympics end. Okay, this is dependent because we ask them a before and after. It's dependent. And we just ask them a question like, do you like it or not? So it's still qualitative and it's dependent. So dependent and qualitative. And because it's dependent and qualitative, we know that we're not talking about independent. This is independent on page 27. Okay. And we're not talking about means, so we know that's not it. So we are talking about dependent and let me get to the right spot in the so because this is dependent and qualitative, we don't have any formulas that we would look at. Okay, we don't have anything for dependent and qualitative. Also up here, we have, this would be the 2 prep Z interval for those. Okay, so just want to make sure that we're paying attention to that. So let's look at letter C. Letter C says a researcher wants to know if basketball or soccer players weigh more. A random sample of male college basketball players and a random sample of male college soccer players were obtained and weighed. Then their results were compared. So we have 2 independent samples. One is basketball player and one is soccer players. So they're independent and we're measuring their weight. So they're independent and quantitative. Okay, independent and quantitative. And so we are looking at our chapter, there are 2 samples. So we know it's not proportions, they're measured. We know it's not matched pairs. It is means, but it's not matched pairs. So we're looking at 2 independent means. So that would be the 2 sample t-test. So the 2 sample t-test. Okay. And then we're going to go to our interval and ask what we would use for the intervals. So that's 11.3, confidence interval for the difference of 2 means, independent samples. We're going to use the 2 samp t interval if we were doing a confidence interval. So 2 samp t interval. And we don't have a 2 samp t interval. So none of these. So we would need to use a 2 samp. Okay. D says, a researcher collected data showing the heart rate beats per minute for a random sample of coffee drinkers before they drank coffee and also 15 minutes afterward. Uh-oh, we have a before and after, and we're measuring time. So this is a paired dependent data, and it's quantitative. Okay, so it's paired, so a before and after, so we're looking at matched pairs. So we're going to run a t-test. If we were doing a confidence, or if we were doing a hypothesis test, it would be a t-test. And so t-test for differences. And then we go to our confidence intervals, we would be looking at a t interval for the differences. It'd be matched pairs t interval for the differences. So right there. Okay. So let's look at our first hypothesis test for 2 samples here. So on page 241, it shows you what's also in our yellow sheet. So let's just go to our yellow sheet here on the 2 prep Z interval, or sorry, 2 prep Z test for independent samples. So it's on page 270 in the gold sheets. And it shows us that we have central limit theorem requirements that we have to look at. So we need to make sure that we have random samples for both of our samples. We have to make sure that they're independent from each other. And then we also have to make sure that they're independent of the population. So individually, the 5% of the population size for each. And then we have to show that they're each normal. So note that the independence and normality we have to show for each sample here. Our hypothesis statement is going to be look a little bit different than what we've looked at before, in that now we don't have a sum value that we're comparing from the population. We're literally comparing sample 1 to sample 2. We still have a left-tailed, a two-tailed, and a right-tailed. So note that the hypothesis statement looks different because we're comparing the 2 samples. There are no values in our hypothesis statement. Step 2 is the same. Step 3, you don't even need to write the formula for me. You just need to give me the Z0. the test statistic. Step 4 is going to look the same. Our pictures are going to look the same. Step 5 is going to be comparing the same with our p-value compared to our alpha, and our conclusion is going to be stated the same. So it's mainly our step 1, how we're going to write that hypothesis test, which you need to be very good at discerning whether we have 2 samples and what type of samples we have. So let's turn to page 242 and look at our very first example here. I'm going to let you read through this for a minute and pause. And once you read through it, we're going to discuss. So this data here is talking about infants that were born earlier than 34 weeks. And talking about their supplemental oxygen for them. So they decided that they were going to give the 2 groups, whether they were going to give them caffeine or not. And this is to help with their having bad outcomes from being born early, and getting this caffeine therapy helps them so that they don't possibly have apnea, okay, where there's no oxygen. This is called apnea. So you might have heard of adults getting sleep apnea. It's similar to that. So our first group is going to be the caffeine group, it says. So this is the caffeine. And we want to find the proportion that had bad outcomes. So that would be, there were 350 out of 963. And then for the placebo group, there were 447 that needed oxygen out of the 954 in the sample. Okay. So we will find out those decimals here in a minute when we put it into the calculator. So it says, hypothetically speaking, what is the good outcome for the premature infant at 36 weeks? So the good outcome would be not needing oxygen, right? So not needing oxygen. So a good outcome would mean, because notice it says that they, apnea of premature defined as cessation of breathing that lasts for more than 15 seconds and is accompanied by hypoxia, occurs in at least 85% of infants who are born at less than 34 weeks of gestation. One therapy for this condition is to give caffeine to the premature infants. Medical researchers conducted an international study in which one sample of premature infants was randomly assigned to receive caffeine therapy and another received a placebo. Okay, so researchers compare the rate of needing oxygen. So the ones that needed oxygen, right, and the ones that did not need oxygen. So these needed oxygen and these did not need. And they needed oxygen and they did not need oxygen. Okay, so those that did not need oxygen. So verify the requirements to conduct a hypothesis test to determine whether the caffeine therapy was effective. Okay, so the first one is, did we have random samples? And we did. The second is, are the 2 groups independent of each other? So yes, the 2 groups are independent from one another. The third one is we have to prove independence by themselves between each group. So the first group, there was 963. Is that less than 5% of the population of infants that didn't get caffeine? So we're just saying of all infants out there with apnea. So yes, there's definitely way more than, so if you thought of this as 20 times 963, you could make sure the N is as big as that. And so 20 times 963. So are there at least 19,260 babies out there? Yes. And then we're going to do the same over here for the 954. Let's do 20 times that. And that comes out to be, are there at least 19,080 babies out there, premature babies? And yes, I'm sure there are. Then the fourth thing is normality. So we are going to check for each of these, right? That N times P times Q is greater than or equal to 10. Okay, so we need to know our P hats. So let's just go up there and calculate those. So 350 divided by 963. So this P hat is 0.363. And this P hat is 0.469. So let's go ahead and check those down below. So we would have N is 963 times 0.363 times 1 minus 0.363. And let's see what that comes out to be here. And that is 222.68. So yes, it's definitely bigger than 10. So that shows normality for the first group of babies. And then the second group is 954 times 0.469 times 1 minus 0.469. And let's see what that comes out to be. And that comes out to be 237.58, and that is sufficiently bigger than 10. So yes, we have met all of our criteria for the central limit theorem. So now we can move to page 243. 243 is asking us to perform, let's just raise this up here. Perform a hypothesis test to determine whether the caffeine therapy was effective in lowering the death or disability rate for premature infants. Okay, so that means we have to state our hypothesis first. So if we're proposing that it has lowered the rate, then we would assume that the proportion for the caffeine rate would be lower because we're thinking that the caffeine's helping the babies. So that's what we're proposing here. So that's going to be our hypothesis. P1, in H0, we have to say P1 equals P2, but we're proposing that P1 is less than P2. And we set our alpha that we're testing at level of significance right here at 0.01. And so we're going to go to StatCrunch and run this and see what we come up with. But let's go ahead and draw our picture so we can kind of get that ready. So our picture is a less than picture. So we're looking for that. And then we're going to be needing our p-value compared to our alpha 0.01. And then we're going to write up our statement here. So let's just go ahead and go to StatCrunch. And StatCrunch, we're going to go to statistics, and we are going to go to proportion stats, and we are going to look at two sample. So proportion statistics, two sample, and we have summary data, okay? And so we have sample 1, successes and observations, and sample 2. So let's go ahead and enter those. We have 350 out of 963. And then we're going to tab down and say 447 out of 954. And this is a hypothesis test between the difference. And notice that it says P1 minus P2. And that's because if you were to compare and put P2 on the other side, it would be P1 is greater than P or less than P2. So we want this difference to be less than 0. Okay, we're thinking that we're thinking that P2 has a bigger proportion than P1. Okay, so we're going to hit compute, and it gives us this printout right here. It validates what we were testing, and there's our Z statistic. It's a negative 4.67. And there's our p-value. It's very small. Very, very, very small. And so we'll just say 0.0001 for that. So let's just go back to our first pat for a moment. So here we are. There is the p-value that came out of that. And we can see that that's definitely, it said it was less than 0.001, but that satisfies enough to tell us that we are going to reject H0. Okay. So there is sufficient evidence. Evidence to support the claim that the caffeine lowers the death and disability or need for oxygen, right? Need for oxygen for premature babies. That's good. So there is sufficient evidence to support the claim that the caffeine therapy, caffeine lowers the death and disability or actually the need for oxygen for premature babies. That's a good thing. So you can see down below, we have the formula for a confidence interval between two independent proportions, and that's also on our yellow sheets. There's a whole page for chapter 11, confidence intervals. And right up here is the one we're going to look at first, confidence interval between two proportions. You can also see there is sample size as well for chapter 7, and that's only for proportions. And we will look at that here in a moment. So let's turn to page 244. So 244 says, researchers from the Pew Forum on Religion and Public Life interviewed 2 random samples of people. Both samples had 1,500 people. In 2002, 645 people expressed support for stem cell research. In 2009, 870 people expressed support. So let group 1 be the 2002. And they're asking us to compute a 99% confidence interval for the difference between them. and find the difference in the proportion of people who support stem cell research in the 2 different years. Just give the result, do not show work. Okay. So let's look at P1 and P2, P hat. So P hat would be 645 out of the 1500, and that comes out to be 0.43. And the second sample P hat is 870 out of the 1500, and that comes out to be 0.58. Okay. So notice that we wrote it this way this time, P1 minus P2, so P1 minus P2. And we just want to know, we just want to predict what that difference is. Okay, right now it looks like P1 is lower than P2, but we'll see how that predicts. So let's go to a confidence interval here. This time I'm going to show this confidence interval right up here. It's the 2-prop Z interval in our calculator. We're going to assume that our requirements are met to do this. So let's go ahead and go to, let's look at StatCrunch first. So that was from our last one. So StatCrunch, we're going to go to 2 proportion statistics, and we're going to do 2 samples again with summary data. And so this time we have 645 out of 1500, and then we have 870 out of 1500. Oops. I got a little quick on my fingers here. This time we're not running a hypothesis test. We're going to do a confidence interval, and we are saying that we want a 99% confidence interval. So 0.99, and hit compute. And there we have it. This is so nice and simple. So there's our lower limit of negative 0.1965 and our upper limit of negative 0.1035. And let's just show this on our TI-84 because I know some of you folks are still using that. So we're going to go to Stat and over to Tests, and we're choosing 2-prop Z interval. So 2-prop Z interval. There it is, letter B, 2-prop Z interval. And we're going to enter just like we did into StatCrunch. So 645 out of 1500. This is so touchy. 1500. And then 870 out of 1500, and then we have to put in a 0.99 and hit calculate. And there we have it. So let's just go back to what it looks like on our course pack. So there it is on our course pack, our lower and our upper. So lower, upper, right there it is. Next, it says calculate the point estimate of the difference in the proportion of people who support stem cell research in the 2 different years. So the point estimate, remember we said we can do, so the point estimate is we're trying to predict the difference between the 2. So we could just subtract the 2, right? So we can just say point P1, which is 0.43 minus 0.58, which is a negative 0.15, or we could also do the upper plus the lower divided by 2. So negative 0.1965 plus negative 0.1035 divided by 2. We learned that back in chapter 9. And we would also get a difference that's a negative 0.15. So it says compute the margin of error using the interval above. So the margin of error is the upper minus the lower divided by 2, the width, right? So the width divided by 2. So that would be negative 0.1035, subtracting a negative 0.1965 divided by 2. And this comes out to be 0.0465. You could have also done the upper minus the point estimate, and that would have gotten you the same. So E says, interpret the confidence interval in context of the situation. So we are 99% confident. So we're using our confidence of 99%. We are 99% confident that the true difference between those that support stem cell research from 2002 to 2009 is between a negative 19.65. I'm going to say percent because it's just easier to understand, and that's a percent, and a negative 10.35%, which means it's gone up, right? Support, let's write that over here. Support has gone up. That's why the 2009 is bigger. And when you subtract the 2002 minus the 2009, it's a negative value. So it says, does this confidence interval suggest that in the news on stem cell research from 2002 to 2009, it really should be, what does it suggest? So it appears it suggests the support has increased. We just talked about that. So to show a significant difference, P1 and P2, the interval. So to show a significant difference, the interval has to include 0. Actually, no, it cannot include 0. So if it includes 0, there is no difference between them. And this did not include 0, right? They were both negative. The whole interval was negative. So to show a significant difference in P1 and P2, the interval must not include 0. This is written a little bit different this time around. So it must not include 0. Take a minute and make sure you've got that all down there. Okay. The last thing we're going to do in lesson 11.1 is look at what kind of a sample size do we need if we want to test two different sample proportions that are independent. And there are two formulas. One, again, if there's a prior estimate, and one with no prior estimate. And this one's kind of lengthy, right? So the p hat of 1 times q1 plus, so notice that this is a multiply, and then we add, and then this is a multiply. So we need to find this product, and add them, and they're in brackets, and then we're going to multiply by our critical value divided by our error squared again. Both formulas must be rounded up to the nearest whole integer, similar to chapter 9. Remember that our error is in a decimal form because our error is a percentage. Okay. So it says, suppose a medical researcher wants to know if there's a significant difference in heart attacks between those who take placebo each day and those who take aspirin every day. What sample size should be obtained if she wishes to be within 3 percentage points with 95% confidence? Assuming that she uses the results from an old study. So we have prior data. That's good. In the prior study, it was found that the proportion who had a heart attack while taking a daily placebo was 1.7% with the daily placebo and 0.9% with aspirin. Okay, so let's go ahead and find that. So the sample size we're going to need will be equal between the two samples. And so we're going to look at here, P1 is going to be 0.017 times 1 minus that, right? Plus 0.009 times 1 minus 0.009. And then we have our critical value, right? So let's just go over here and do our critical value. And they wanted 3 percentage points at 95% confidence. So alpha is 0.05. And so alpha divided by 2 is 0.025. So the critical value of 0.025, we could look up using a normal curve, but we haven't practiced much with our gold sheets. And our gold sheets used to have our curves, but I think that they took them, oh, nope, there it is. So our gold sheet on page 265 is a quick way. Up here is for t-table, but your very last row is the z-table, which is nice. So we're looking at 0.025. So we're going to go to the column that says 0.025, which is actually right here underneath the area. So 0.025 all the way to the bottom number, 1.96. So 1.96 goes here. That's our critical value. And our error, they said, was 3 percentage points. So that's 0.03. And then we're going to square that. And when we put all that in, that comes out to be 109.4. But we always round up to the nearest whole integers. So we should have sample 1 and sample 2 should each have 110 values in their data set. So remember to put brackets around the outside here. So it's very critical how you get this typed into your calculator. If you need help with that, let me know. Now we also want to know, what would the sample size need to be if we don't have any prior estimates? So we're going to use this formula up here, which is much more simple, 0.5. So N1 will equal N2. So 0.5 times the same critical value, 1.96, over the same error squared. And that one more simple. See if you can just follow along here. So 0.5 parenthesis, and I'm going to make a fraction here. And we have 1.96 over 0.03. We're going to square that, and it looks like 2134.2. So 2134.2. So we're going to round that up to 2135. So we did a lot in this chapter, this section already. We looked at hypothesis tests for 2 proportions that were independent. We looked at a confidence interval for 2 proportions, and then we also looked at sample size. So meet me up next for lesson 11.2.